Cheers, Chris. Yeah, so it's my pleasure to get up here and present this. So what we want to talk about is what's underneath Australia, but also what's at the surface. So I want to take you through understanding the lithosphere, why it's important, and then take you through only a small part of my PhD work. What I've chosen to do today is, rather than bombard everyone with all these different data sets that tell us different things and then try to integrate them, what I thought I'd do is take you through a case study of how you can think very carefully about the problem you're trying to solve, all the different holes within it, and then still get something useful out of the end. And that resulted in the first paper out of my PhD. So in terms of my acknowledgements and starting off with everything, Brian is definitely my long-suffering supervisor. Brian actually retired before I started, so I'm essentially his final student. I'm not sure who regrets that more, me or him. We haven't decided yet. But it's been a very excellent collaborative relationship. And obviously GA and especially Chris have been strong supporters in my time over at ANU. So I spent 3 years over there, then came back to do some things, and I'm now just wrapping it up. So the story that Chris alluded to is I was recruited by Barry Drummond, who then nicked off before actually taking me on as one of his staff members. And so Barry and Bruce Golby interviewed me in the cafe. I was sitting next to a pole, and I came from a job where I had to wear a suit and tie every day. And everyone that has seen me at GA would find that very difficult, very hard to believe. But I definitely did it, and I was wearing a suit and tie that very day. Chris came in his usual no-tie attire, and mentioned to Barry, "Who's this? You can't employ him. He's better dressed than me." So from then on, I've gone for a much more casual and relaxed approach at work, but only in terms of my dress sense rather than anything about my work. And I definitely have to thank both Barry and Bruce, but also Russell in terms of pointing me in this direction. And this direction is actually where what I really care about is the fact that geophysics is always wrong. So I'm going to start with something controversial. The idea is we need to understand how wrong it is, minimise how wrong we are. We can never make it right. There's so many uncertainties in it. And understanding that uncertainty actually gives us a fair amount of power of the data. We can actually then start to use that more scientifically once we understand it, once we get away from the concept of just a single result. I don't know if anyone speaks Latin. Anyone in the audience want to hazard a guess what that actually means in terms of that quote? It's actually a fairly famous thing in mathematics. So if you put that through Google Translate, it says, "This margin cannot contain." So this is Pierre de Fermat's statement about what ended up being his final theorem. And the reason I've got that up is I can't hope in 50 odd minutes to go through all of the aspects of the lithosphere of Australia. So this will only be a very simple flavour of a few aspects of it, why it's important, and then a case study. But there's definitely a lot more detail, and I'm by no means the only expert on the Australian lithosphere. So this is something where much more information could be provided than I can actually fit within this talk. So again, just to reiterate, I want to go through what is the lithosphere. I'm aware that not everyone thinks about it on a daily basis. So I want to go through what it is, what its properties are, how you might actually measure those properties, and then how we need to go further in understanding the Australian lithosphere. So one of the more famous t-shirts that I actually have is an excellent one here, which is a lovely cake of the Earth. And people think it's all about layer cake stratigraphy, but the Earth is a cake at many scales, and fractals will be something we touch on later on. But at multiple scales, at the small scale and at the large scale, you can actually think of the Earth as a cake, which hopefully makes this talk a little bit more digestible. When I talk about the lithosphere, and that was a joke for James Johnson, our Chief of Division, who does appreciate a fantastic bit of pun, and there will be many throughout this talk for James. Wanted to make sure there was something for everyone. Lithosphere is actually something that was introduced to me in first year by one of our UTAS lecturers, Clive Burrett, who loved to kind of spell out all of the different words and talk about where the name has come from. The lithosphere really means rocky sphere. So this is the rocky part of the Earth up at the surface. So it is the crust and the uppermost mantle which at relatively short timescales and even to moderately long ones we can think of as being solid. So this is truly the really solid part of the Earth that we interact with daily. So there's a bunch of misconceptions that we'll go through about the lithosphere, but that's the bit we're talking about, that upper bit. So the upper oceanic area is not that thick through to a couple of 100 kilometres potentially in terms of this rocky part that we interact with daily. The other thing I mentioned is architecture, and I don't mean that in terms of classical architecture or architecture such as the GA building. I'm talking about the arrangements of the components of Australia. So Australia isn't just a continent that came into being 4.5 billion years ago when the Earth first formed. Australia is an amalgamation of a bunch of different areas, which we'd call geological provinces, that derive their properties from their history. So the types of rocks you find in a province are really determined by how those rocks came to being. So if they're sitting in an active margin, they're going to have completely different rocks to sitting as a sedimentary kind of thing off on a passive margin in plate tectonics, sort of speak. And these are a couple of views that most people would be comfortable looking at. So one is the surface geology of Australia and some shorthand for some of the different provinces. And then once you actually think about the more solid parts and divide them up by age. There are a lot of areas that I kind of refer to a lot. The Yilgarn Craton, kind of solid core of this southern part of Western Australia here. The Pilbara and also the Hamersley Basin, host of a bunch of iron ore, fairly important, but a bunch of other areas. So you have the North Australian Craton, amalgamation of a bunch of different provinces there as well. We also have the Gawler Craton here in South Australia. So I'm referring to some of these boundaries, so I wanted to put it up first and foremost so people can kind of get an understanding of the arrangement of Australia as we kind of understand it from the near surface. We'll be looking a little bit deeper, which means some of these boundaries, which are defined more near surface, may not necessarily be exactly the same. So I polled a lot of people about this, both before I started my PhD and then throughout my time, and finally when preparing for this talk. And there were three main themes that came out of me saying, I'm going to talk about the lithosphere. And the first was, it's too deep. It's beyond explorable depth. It's the first thing most people talked about. The second was, people pointed out that they felt it was only of academic interest. This isn't something that influences anything other than some academic study of the Earth. And finally, and this is something I'm most happy with because as a physicist, we can kind of test everything that we can get a physical response from. But it's not like you can go out and test what you find. So that was a kind of accusation. Of course you want to do a PhD in that, you can say whatever you want. So I want to go into this segment where, again, another pun for James, I want to bust some myths about the lithosphere. Separately, breaking of the lithosphere is actually an important process in the formation of continents or the breakup of continents. So it's a separate kind of meta joke about it. So is it too deep? Well, hopefully what I've just talked about at the start kind of illustrates it kind of isn't. We actually stand on the lithosphere. People don't think about it, but the lithosphere is both the crust and the uppermost mantle. And that crust extends all the way to the surface. Now it has a bunch of other surface processes going on it to modify it, to weather it, to give it different properties, but it is exposed. Where you have uplift of mountains, that is a lithospheric process occurring. You interact with that daily. That uplift, the rearrangement of plates, even drives the much broader, longer timescale of the changing climate of the Earth. So these are important aspects. I mean, it's not to trivialise that. One of the reasons Australia is so warm and Antarctica is so cold is the opening of the Southern Ocean. And that essentially blocks off the cold air from coming up to the Australian plate. As we've headed north, Antarctica's headed a little south, we opened up the Southern Ocean. That was something that occurred between 40 and 25 million years ago, and that's a lithospheric scale process. It's oceanic lithosphere, but it's lithosphere nonetheless. So the lithosphere is definitely something we interact with daily, something we certainly need to consider, and not just the near-surface components of it, because what is occurring at depth does have an influence at the near surface as well. So, as I said, topography tells us about mass. So if you put a bowling ball on a mattress, it's going to sink somewhat. That happens when you build up a continent. It's going to sink somewhat. The process of understanding that and how it compensates mass is isostasy. One of the largest contrasts you actually see when you look at seismic reflection lines, and most people would be quite comfortable with this, would be the MOHO, which is also something that we need to understand to be able to locate earthquakes that are beyond some 20, 30 kilometres away from your seismic station. Those earthquake waves go into the mantle because it happens to be faster than going through the crust. Another component, and one which I will actually touch on in this talk, is once you remove the fact that the Earth has a natural magnetic field coming from the core, the final signal that you get, if you walk along with a compass, it's going to deviate ever so slightly. It was the first geophysical exploration performed by the Greeks. They would walk around with something called lodestone. Hanging off a string, it would point towards more lodestone. Lodestone is magnetite. So the way you would actually prospect for iron ore back at the start of the Iron Age was to use the induced magnetic properties of the Earth. Those magnetic properties are bound where the Earth can remain magnetic. So that's another aspect that actually influences us from a daily basis. There is actually aspects around hazards due to conductive bodies as well that would change, induce spikes and things in the geomagnetic field, and that again can come from the lithosphere. So it's only of academic interest. I'll touch on that next. This is a surface geology of Australia. So Australia's kind of dominated by quite a lot of cover sitting over here. So we've got some of the rock where it's cropping out, and then we have all of this kind of covered area. If you actually look at where the major mineral deposits are, the things that drive our wealth, they occur, where we find them is where the rocks stick out of the ground to a large degree. We can start the search a little bit undercover, but there's quite large tracts of land that are covered, some of which is relatively thin cover. For us to understand what is occurring out into these margins, we need to understand the lithosphere. Another component of that is the timing of ore bodies, where you get certain types of ore bodies. So where you get gold in Western Australia is strongly controlled by age. And that's actually something to do with the geodynamic processes occurring at that time of Earth history. I don't want to go into arguments about different aspects of plate tectonics throughout history, but the important aspect is there is a temporal relationship, and that temporal relationship relates to lithospheric scale processes that are occurring. So the arrangement and driving forces. The other thing to consider is that while that's important in terms of age, ore formation involves all of the lithosphere. Not everything we want to find happily lives in the crust. Certain minerals that we need are more favourably able to occur in mantle-related sort of settings. So to extract them, you need some way of getting those fluids up. Not every ore deposit is formed with fluids that occur in the near surface. Even some of the aspects of heating of the Earth that then drive maturation of petroleum provinces can be heat derived from relatively deep. It doesn't have to be near surface heat. So that drives the resources. Where some of these breaks can occur are going to drive the formation of basins. They're the sorts of areas where groundwater is hosted. So understanding where those more hidden things might be underneath the thin veneer of cover is around understanding the architecture of those major changes in the lithosphere. But I'll bring it back to cake. Everyone likes to think about cake, especially on a Wednesday. So although I've talked about the lithosphere and how important it is, not every aspect of the lithosphere is going to be fertile for different ore bodies and things. So you do need to consider all aspects of it. So if you think of the lithosphere as being the flour, the kind of the bulk of what makes up the cake, if you want to have what apparently is the prettiest vanilla cake in the world, according to the reliable source of the internet, you might want to throw in a very small amount of vanilla as well. And you need to have all of those ingredients to end up with your prettiest cake in the world. So you need to consider how all these things interact. So it isn't just saying, well, if you want to find these things, only think about the lithosphere. But certainly, if you want to make a cake, don't forget the flour. Another aspect, and this goes back to the things that you can interact with, the lithosphere isn't testable. So if you want to understand these things, this isn't testable. And I find this kind of funny because I've had somebody who told me that who also accepted that we could measure gravity waves. And if anyone could tell me that it is much easier to measure gravity waves than measure aspects of the Earth, I'd really like to have a conversation with them about fundamental physics, because that's beyond string theory. However, areas in Australia, so things like the Glasshouse Mountains and the volcanics occurring underneath there at the back of Brisbane, they are the result of lithospheric scale processes. They are not something that just came into being because the Earth felt like it. There are aspects of the geodynamics of the Earth that drive that. Or the Flinders Range is potentially uplifted today. And that brings in seismic hazard. I brought in a declustered view of events, so you get rid of lots of earthquake clustering because it's a little bit easier. This is from the most recent earthquake hazard map. But the elements of Australia that are seismically active are driven by aspects of the Australian lithosphere. Another aspect of the lithosphere that people may not consider is, at some point, the Earth gets too hot to shatter. Now, a few people have just kind of looked at me very strangely, and it was the same look I had in second year when that was introduced in structural geology. But if you consider, at some point, the Earth has to become plastic enough for plates to move, and at the surface, it's very brittle. Otherwise, if you bashed a rock with a geology hammer, it would never shatter. It would just kind of mush together. There is a change that occurs at some point, and earthquakes occur by breaking the Earth. Now, there's aspects about strength and timescales that I don't want to go into, but at some point, the Earth ceases to be brittle. And that depth is the maximum depth you would expect earthquakes to occur. In a continental setting, where you're only thinking about quartz, it's about 350 degrees, some 12 kilometres depth with kind of natural geothermal gradients. So that has an influence on earthquake hazard and shaking. So if you're in an area where you have a much more subdued geothermal gradient due to a much thicker lithosphere, you may well expect earthquakes to occur at a greater depth. Or conversely, if you're in an area which is much warmer, they could potentially occur at shallower depths. There are also other areas where you can exceed that through potentially fluid flow, and there are papers on the Flinders Ranges that indicate that maybe we have earthquakes occurring all the way into basically the base of the crust. So understanding the lithosphere and what's going on is a fundamental influence on the hazards which interact with us daily. So it certainly is not something that's testable. It's testable every day, and the Earth shows us. We just need to understand what it's telling us. This is going to be more contentious, but it gets back to gravity waves. Another aspect of the fact that it is testable is we see expressions of that in different measures of geophysics. Now, you can argue about the magnitude, but the results are definitely there. So in the early 1900s, it was recognised that there was a velocity change based on distant earthquakes. So that produces something called the Mohorovich discontinuity. We can see that on reflection seismic, where we suddenly go from lots of reflections to potentially this sharp boundary, or maybe even this much more washed out boundary, where we're changing from the crust into the mantle. And that strong reflection, package of reflections, is actually due to the velocity change across that interface. So that velocity change drives earthquake waves to want to travel through the faster mantle rather than through the slower crust. So once you get to a certain distance, the waves are going to either propagate along or down through there. And that discontinuity is recognisable by how fast earthquakes will get to you compared to where you expect it. So understanding that definitely is testable, but then measurable in a different piece of geophysics. Another one is to actually start to measure velocities. Now, when I say measure, everyone's going to be going, it's tomography, that's not measuring. Absolutely is measuring. It's just a very large volume of the Earth that you're measuring at once. And the signals are very subdued, and they're smoothed by the fact that they go through the Earth. This is definitely testable. You can simulate those conditions in a laboratory, and you can measure realistic materials at mantle temperatures and pressures, and you can measure their velocities, and this is about their directionality. You can measure both of those aspects in a laboratory and reproduce this kind of scale of results. So absolutely it's testable. It's testable at a laboratory scale, it's testable at the scale of the whole crust, and I would argue also at the whole scale of the lithosphere. So I'll go back to cakes again. Obviously it was what I was thinking about when I was writing this. So what I've talked about are the different properties of the lithosphere, and I've touched upon them. So the lithosphere has particular properties about seismic velocity. It has particular properties about density. It has particular properties about magnetisation. It has particular properties about strength. All of those properties can be thought of, much like a cake, as bound by layers. So we have topography, and this is just some arbitrary cross-section that I drew. So neither believe the relationships I showed nor the kind of scales or anything. This is not scale or even correctness, it's just to illustrate the point. So you've got the surface topography. We're all kind of comfortable walking up mountains or going down valleys. Some people may also be comfortable with the fact that the crust isn't the same thickness everywhere. It gets particularly thick underneath Central Australia. It's very thick under the Himalayas, where you have two continents on top of each other. And it changes in thickness. You might have a thicker crustal root compensating for a mountain. That's our type of isostasy. Or you might have some density changes accommodating that further over here and where it's actually getting shallower. All possibilities. This is something we can measure even with just the arrival times of earthquakes. This is not something that required computers to measure. This is something you could work out on pen and paper in the 1900s. In much the same way, you can also use earthquakes to suddenly realise there's another point at which the Earth changes velocity, and that's the lithospheric boundary. So that's where we go from the rocky part to the bit that's kind of convecting and moving around. So we can definitely recognise those. And they are layers which have distinct seismic properties. And I've touched on it, they also have distinct density properties. So the density is the mass that sits within a particular layer, because it's got a certain volume, and that actually influences the gravity. So for those that don't kind of understand too much about geophysics, you can weigh ever so slightly less by going and standing over a particular rock. And I use weigh in a very particular physics term rather than mass. Your mass never changes, but your weight, which is the product of your mass and the acceleration due to gravity pulling you down, changes. And in Australia, that changes by about 1 part in 1,000 once you take into account the shape of the Earth and things. So when you go to some parts of Central Australia, it has particularly low gravity, and partly that's due to changing crustal thickness, where you have a low density here and higher density here. Where it's thicker with the low density, you get low gravity. But it can also be the result of lower density from different rocks. But while we're talking about properties, there's also properties of strength that I alluded to before. So this is our layer where earthquakes may well occur. Now there's a lot of arguments according to which group and which university you went to as to how deep this will be and where strength is contained and where earthquakes could or couldn't occur. But at some point you don't get earthquakes. And that's very different to other planets. So the moon, you actually get very strong earthquakes very deep. And that is something due to the fundamental structure of the moon. So we can certainly bound our properties of strength. We can also bound our properties of the base of magnetisation, which is what I'm going to go through in a moment. So in terms of what I've kind of talked about in this first part of the talk, the lithosphere, hopefully you now understand, is of critical importance. Understanding it drives our understanding of resources, of hazards, of how we interact with the natural Earth. So it is absolutely of critical importance. The other kind of thing, and where I'm going with this, is that the properties of the lithosphere, some of the changes in the lithosphere, relate to the history of those particular areas of the lithosphere. So areas which have been extended and thinned will have different lithospheres. So something like the African rift today will have different lithosphere to somewhere like the middle of an ocean. We'll have different lithosphere to Western Australia, to Eastern Australia. And it all relates back to the differing history. So the kind of main argument of where I'm going with this is by understanding the lithosphere and by mapping these changing properties, we can start to map where those different parts of the lithosphere are, even where they're covered, so where we might not recognise them. The reason that's of critical importance is if we want to go out and we want to start to look for the equivalent of our car keys underneath the couch, we need to know where we're going to start to look. Where was the last seat we sat on? Where was the last part of the Earth that was active for the types of mineral deposits we might be looking for? The other aspect is most of those properties are bound within these horizons. So the fundamental constraint on those properties is to understand the geometry and the architecture of these horizons, and also their uncertainties, because they're absolutely very uncertain. So with that in mind, I'm going to take you through a case study, and this is how you turn somebody else's paper where they looked at a very small component of the US and apply it to Australia. So absolutely general kind of interest. So if you're not just into the geophysics, hopefully I can kind of sell it as a much more important, bigger picture kind of issue. So I talked before about the base of magnetisation. Magnets aren't always magnets, and that's something that I'm actually aware of in that one of my hobbies I like to do various times is to work on various old motorbikes, and a kind of way that they're assembled is that the bit that provides charge to keep everything charging is a bunch of magnets spinning around on a flywheel, and that's pressed onto something. And the naive person trying to get that off would just heat it up and pull it off. If you do that, it will no longer charge, and it's because you stop the magnets being magnets. And all magnetic things have a property called their Curie property. And in case you're curious, another pun for James, it's actually related to Pierre, not Marie. So Pierre Curie discovered something which is a phase change in magnetisation, which at certain temperatures, different things stop being magnetic. So there is a temperature effect. However, and this is something I want to argue later, there is also a compositional effect. So at the minerals we talk about for crustal magnetisation, there is a very large range of Curie, or Neal if it's a different type of magnetisation, where it ceases to be magnetic. So for magnetite, which is the strongest magnetic mineral, that stops at about 570, 580 degrees. So once you heat magnetite beyond that, it will no longer be magnetic. But if you add some titanium, you actually dramatically decrease that temperature. So there is absolutely a control on titanium. There's also a control in terms of the iron sulfides in the pyrrhotite. You add more sulfur to pyrrhotite and it also decreases both its temperature and its magnetic susceptibility. So the ones we really care about are these ones in bold. They're the ones that we can detect geophysically in our magnetic anomaly maps. And the reason this is important is that's the Curie temperature. Within the Earth, we have the geothermal gradient. As you go into the Earth, it generally gets warmer. And that's this geothermal gradient. So once you reach the Curie point based on the geothermal gradient, you then get to a Curie depth. So that's the depth at which it ceases to be magnetic. And I'm going to use Curie depth and base of magnetisation interchangeably because potentially it's not just one particular temperature. So base of magnetisation is more correct, but often I might slip back to Curie depth. So this is a bit of a primer, and hopefully I can make some sound work, but this is something I did to kind of let people understand changing into the frequency domain, which is an important process about how we actually study these. So Mary had a little lamb. I sat down and basically synthesised that and the notes, also played some chords along with it and recorded it. And this is what you would call time domain. So this is time increasing along here, and this is the loudness, the amplitude of the sound wave with respect to time. If you break into a very small part of it, you can see it's all these little sinusoids. Now there is, Fourier's theorem is that you can represent anything as a sum of sines and cosines, and you need to go into imaginary numbers and all manner of really cool maths, but essentially any function can be depicted in that way. And you can apply that to real data. So you can take your data, record it in time, and you can perform something called a Fourier transform. And that turns it from being in time and loudness space to being in its amplitude and phase, because it's an imaginary number, but you have frequency. So in this case, this is with respect to time, so they're hertz. So cycles every second. And that's our amplitude. Now, little known fact is that I almost did audio engineering. I was very close to working in a recording studio. I actually spent a year doing that for work experience after school. And each of the individual notes in the kind of Western musical scale have a frequency. They double every octave, and 261.3 hertz happens to be middle C. So you can actually see each of these peaks in amplitude, and they are the musical notes making up both the melody of Mary Had a Little Lamb, and then underneath it, some of the chords. And if you actually take this further out, you'll also see the harmonics of those notes. But I wanted to remove kind of that complexity. So this is where we convert something from some representation in time into the frequency domain. But being good mathematicians, they realised they didn't just have to restrict themselves to time. You can perform this in a line. Basically, if you measured, say, magnetic properties along a line, you can then take its frequency transform, much like we did for the music, and that will give you the frequency of the changes in the magnetic properties. And you can do that in 1D, or you can do that in 2D. You can do it in any dimension you want, but it gets really hard to visualise. So we will talk about spatial Fourier transforms. So this is where we convert from spatial dimensions into spatial frequency. So they are how do things change with respect to space. So much like a high note changes very rapidly with time, or a low note changes very slowly with time, a long wavelength in space will change very, very slowly. A short wavelength in space will change very rapidly. The reason this is important is things which are close to you have higher spatial frequencies. Things which are further away or wider, there is some ambiguity, will change much more slowly. So as we're talking about the lithosphere, we're talking about looking for the low notes within the music. So if you hang out in Braddon on a Friday night, you're hearing people drive along with their fully sick cars, you're listening out for the big subwoofer notes. That's what we care about. We care about the shaking of the car. We don't care about the little hi-hats and little cymbals on top that just add a bit of flavour. We want those broad, low notes, those broad changes. Another thing which is a trap for young players is that's the X direction, that's the Y. When you transform it, that's the X, that's the Y. So you can actually be rotated by 90 degrees. The other thing that gets really fun is that's zero frequency, so that's something that doesn't change over the whole image. And then we're going to positive Y frequencies, positive X frequencies, but we also have negative frequencies. And if you're dealing with only real data here, there's some symmetry and some other things you can exploit, which are really handy. But it is something where you have to be very careful about the representations. Another aspect you have to be very careful about is the assumption is that you have an infinite representation of this. And we don't have that. We don't measure geophysical properties on an infinite scale. So there is uncertainty that comes from that process. But fundamentally, what I'm going to be talking about is converting data from a spatial domain and dealing with it in a frequency domain. So one of the ways in which you actually see that is if you look at images which hopefully most people are accustomed to, and I've presented them on different colour scales just so that I can make a point, not just because Brian likes different colour scales, but those who know him will recognise that he does like to do things differently. So this is the gravity data of Australia, unfiltered, and you actually see the thickest part of the Australian lithosphere is represented with this gravity low, really broad gravity low. So that would actually have a long wavelength sort of feature. There's a bit of trickery that I do behind the scenes to do some multi-level averaging. So these are actually represented at the same resolution. So normally people would look at these and go, well, the magnetics looks different with gravity because that's at 80 metre pixels and that's at 800 metres. These are actually balanced already in terms of their cell sizes. And yet we can see way more little content in the magnetics. And that's because magnetics falls off with what we would call the inverse cube. So as you take a magnetic source and you double your distance from that magnetic source, you will see 1/8 of its signal. Gravity, on the other hand, falls off, if you know Newton's law of gravitation, with inverse square, which is actually the same way sound waves fall off. So if you double your distance from a loudspeaker, you get a quarter of the sound. So this falls off less with depth than this. So fundamentally, we're already sampling different depths with these two data sets. But thanks to having things in the frequency domain, you can do some really cool things. Like you can do something that would be impossible to represent in the spatial domain, and this is the horizontal integral. And you can start to see they now have very similar frequency contents. And that's because doing this integration process has actually given us roughly the same depth dependence as the gravity. And you start to see this broad kind of feature matching in through here. So that's all well and good, but you can also go the other way. So we can take this thing, and it's got a faster depth dependence than this, and we can make this thing by doing some derivations, we can basically make it have a faster depth dependence, and we can start to see some similar frequency content. But we can also see some differences that just aren't mapped. So this particular fault through here doesn't really come up in the magnetics. Likewise, the extension of Mount Isa underneath cover doesn't have quite the same expression in gravity. So there's aspects about their different properties that we can measure. So that's all cool. That's one way of probing the lithosphere, is you can just think a little bit about how things change with depth and try and balance them. So we've now got real happy spatial wavelengths and things, but what we need to do is use that to tell us something about the magnetic properties of the Australian lithosphere. So I like to do things simply. It's partly because I'm not a complicated person, and partly because I think there's a lot of elegance through thinking about things from kind of first principles. And there will be a test on what all of these symbols are at the end. So I hope everyone's read up on the second order real number Bessel functions, because that's included. Anyway, this happens to be a really nice integral solution for a particular model of magnetisation. And that model of magnetisation is depicted here. Doesn't need to include the tree, could be water. But I just want to say surface of the Earth. You have some thickness, which is distance to top, before you get to a layer of magnetic properties. So in Australia, you might have non-magnetic sand sitting on top of a magnetic basement. Within that magnetic layer, with this particular thickness, you have a number of magnetic sources. And those sources are randomly distributed, but with a degree of self-similarity that is going to be a whole different dimension for people to think about. Essentially, the geometry of those is captured by this parameter beta. So you can think of it as thickness to the, basically depth to top, essentially depth to base, because you've got that plus that, and then you've got how are they distributed in their geometry. And finally, that's measured at a number of spatial wavelengths. There was a reason I played Mary Had a Little Lamb. So that's all well and good. I've always hated seeing mathematics equations and then not being able to visualise what they actually look like in terms of their response. So this is, we'll call it wave number. It's basically wavelength stuff, but low notes, high notes, low notes, high notes, low notes, high notes. And that's for depth to top, differing thicknesses, different geometries. So the first thing hopefully people notice is depth to top, they deviate the most at the high notes. So if you want to distinguish between different thicknesses of cover, you need to prioritise understanding these highest notes of the music. So you would get your equaliser and you would get rid of everything low, you'd boost everything high. On the other hand, Braddon, Friday night, fully 6 subwoofer, if you want to understand the thickness, you want to be down in this area. You'll also notice that there is some degree of change here that also occurs for this parameter. So these two are to a degree correlated. That's just the physics of this particular model. But you can start to pull those relationships apart to understand different things. So the other part is all geophysics kind of modelling relies on observed data. Here's how you actually get it, because most people don't go through this in a good way. But you will get out some data from a particular area. That's the data. Fourier transform, real and imaginary numbers. You get a power spectra, which is that cross-shaped thing I showed you before. Do some averaging. You average it around different wave numbers. Then you compute some statistics. It was pointed out to me the kind of weirdness of it being noisy here and not up here and the average being flat. It's because most of the data is very close to that number. But this noise here actually kind of contaminates all of the spectra. So one of the processes I did is multi-level averaging to kind of use this information to boost up our certainties around what's happening here. Because, again, high notes, don't care about them. We can use them to understand the lowest notes. So we can look at some of the smaller scale changes to understand how much information we have in those low notes. So when you're mapping this kind of thing across the continent, you do something called moving window. And these aren't representative sizes of window, they're just easy to draw. But you will have a particular area that you will select. You'll get some data from that. You've got your reserve data for that area, and then you move it. And the reason for that is if you just take the Fourier transform of this whole image, you have the frequency content of the entire image. So what you're looking at is the whole area. You need to do some localization unless you just want to study the continent and just the continent. So you do this kind of moving thing so you can kind of understand where it all sits. The other part that a lot of people in the audience may not kind of think about is what we call geophysical inversion or geophysical modelling. So there's two kind of major steps you do in geophysics. So you can simulate physics. So you can say, here's a distribution of mass, tell me what its gravity response would be. Here's a distribution of magnetic minerals, what are their response in terms of their magnetic intensity? So that's the Ford problem. So solving that is what we've done. So that model that I showed you before, all those funky graphs and that awesome thing with the second order Bessel functions, that's this. That's basically saying, given some property of magnetic stuff, give me some observed data. The other thing is we've extracted a bunch of observed data, and we want to know how well we fit that. And that is what we call the inverse problem. So a lot of people would set up an inversion as some function where you're trying to minimise the amount of difference between what you predict and what you observe. Because that's particularly poorly determined, because you always have way more unknowns than knowns. I don't want to go down a Donald Rumsfeld path, but you have to do some smoothing, you have to add some penalties, so you might say, you know what, I think I was mostly correct, so don't go too far from that. So mathematically, you try to minimise this thing. And that's a very perilous thing, because it's very difficult to find the minimum of something. And I decided to go in a completely different direction, and that was ask the question, why restrict yourself to one model? And in fact, this is an argument from essentially trying to understand an argument between two Richards, one of which wasn't me. Well, in fact, neither were me. So essentially the argument was, can you actually map the base of magnetisation? And in one camp, people go, absolutely, you can see something in it. And in the other camp, it's so uncertain, your inversion could fall into a local minima and you're never actually in the true model and you could have something, so your uncertainties are massive. So with only 4 parameters plus a constant of integration, so 5 parameters, you can then say, well, let's look at all of them. For every single cell, let's look at every possibility. Now, you've obviously got to discretise it, but I tested something like about 50 million models for each individual window of data, of which there were something like 800 across Australia. So consequently, I used a lot of the NCI for a while, which was excellent. But it's something that you can do, something relatively dumb, repeatedly. And so you do that across the whole thing, and you sample the entire space. So I could then choose only solutions that were replicating within the error the data that I was getting. And I could plot up all the things. I thought I'd do the spectral property because it actually looks the nicest. But you get a nice peak for that. For depth to top, it's really not too bad, but it kind of tails off. And for depth to base, you actually kind of asymptotically end up at a point where you can't determine because you don't have wavelengths. You don't have low notes deep enough to see that. So you can kind of do that. The reason that's really cool is you end up with an ensemble of inversions, and this happens to be one of 10 million views of the country. This happens to be weighted by inverse misfit, so the better it fits, the more it's upweighted, and the worse it fits, the least. Smooth it out a little bit more. If you look at the mode, because it's so noisy, you will get these kind of like big cliffs. And the other thing is you get a measure of uncertainty, and you'll notice we're going from 15 to 70 kilometres, and our standard deviation is kind of like 7 to 13 in a, one spot. It's about 13 kilometres, roughly 8 to 10 kilometres. So yes, you can't determine every little step within it, but you can absolutely determine some of those major colour changes. And they're changes where the base of magnetisation is different, and absolutely different, assuming my model's correct. So there is that small caveat. Does it fit with the temperature? Hey, that big gravity low for the thick lithosphere, which is cold and old, absolutely kind of is thick, except for the Pilbara. And I'd probably argue that's something about the composition. Maybe we've got a little bit more titanium because that'll kill the temperature and then therefore kill the depth. New England's pretty funky and a bit hard to understand because it's very thick but kind of new. But that's also the hardest part to determine because of the shape of the kind of continent over there, so it's a bit more difficult to kind of sample it as rigorously. This hot bit here, absolutely see, this bit up here is kind of an artefact of the fact you've got drilling there and only up there, so it's sort of represented in there, but it's much trickier. But absolutely we have some commonalities with temperature. Another thing most people would argue is that magnetisation stops at the moho. Maybe it does in some points, but it definitely doesn't in that old and cold bit. So where you're looking at the Yilgarn, you've absolutely got magnetisation deep, well, within at least 10 kilometres deeper than the Moho in that particular area. And partly that's because crustal thickness is slightly shallower than maybe you'd expect, as you can see here in the Moho map, but also there is some aspect of mantle magnetisation. So the source of that is something for people to continue to argue about. Up here we've actually got this kind of bit where we were much, the Moho was way shallower, and there is probably an extra boundary in there which Christian Sippel from RSES has actually written about. So maybe we actually saw something. Fundamental thing to take away from this is actually, if you want to do temperature modelling, because there's some compositional effects, use the Moho. It's actually more certain. But you definitely have a different measure of the temperature distribution within the Earth. So that's cool, but we've also got this other property. So let's have a look at that. And the reason this is particularly interesting is it really does match more of some of these areas. So you could ask why. And it's actually that beta in terms of its geometry and dimensionality, and it's not an easy thing to get your head around, but it basically depends on geological environment and it depends on dimensionality. So one kind of dimensional sources, Tasmania, Jurassic dolerites, flat, planar stuff, beautiful. Two-dimensional, long stripes through the Yilgarn coming up. 3D, and that's actually because you've got a basin with a varying geometry on top of a variable basement. So you're getting that. Beyond 3, you're beyond 3 dimensions. You're actually looking at like vertical dimensionality and randomness and things that get really complicated. So the original crustal elements map from 1994, those boundaries underneath cover were picked on magnetic character based on qualitative interpretations. But absolutely, you could quantify that character. You could do exactly the same for Russell and Michael Dublier's major crustal boundaries that they picked from the seismic and then extrapolated using all of the geophysics. Some of those boundaries, you can also start to see some of the changes. So here is a way you could actually quantify it, and that's all by thinking very carefully about your model space. So if you combine the two, you kind of get a view of Australia like this, of some cold bits, with some particular character, with some variations that relate to different parts within those areas. And you also get, this major kind of thing of the Eromanga. You really highlight the undercover extension of Mount Isa as well. So it really pops out. I just did this to kind of sum it up, and that is, if we're going to look for things that are underneath relatively shallow cover, that are a little bit special in terms of their magnetic lithosphere, Central Northern Territory and then kind of bleeding out here, and also the undercover extension of Mount Isa, that's pretty cool looking. And also the bit where the Yilgarn changes to the Gawler. Because at some point this has to stop, that has to start. The question is what's between them. What you really get a sense of is Yilgarn, Albany-Fraser, it's kind of Proterozoic margin. There's a bit of Yilgarn poking underneath. Then we got one thing there, another thing there, kind of margin of the Gawler, and then the Gawler itself. So we're actually starting to break up that sort of thing. And it matches very nicely with a seismic line which is shot across there. So absolutely there's a couple of areas that if you wanted to look for special bits, that's where I'd go. So that's all well and good, but now I get to sell my soul for the last minute, and that is talk about, this is a Sir Harold Raggett Award, 70 years ago in a couple of days, so 10 years and a bit. The vision for BMR, among other things, was to map Australia, not just geologically, but geophysically. So in the ongoing 70 years, we've acquired magnetic data that essentially we produce a map which is every 80 metres. We have topography from the shuttle radar at least at 30 metres. We've got better stuff than that. We've got aster-mineral mapping from satellites, so we're measuring chemistry from space every 30 metres to 45 metres. We've got radiometrics data every 100 metres. Got gravity data every 80. Seismic velocity out of RSES is kind of on a scale of every 50 kilometres, but it's missing the big property, conductivity, which is the property that varies the most over the Earth. Fortunately, we have something to do that. To shine the light is AusLAMP, the Australian Lithospheric Architecture Magnetotelluric Program. These are the sites we've acquired. We're actually just starting southern New South Wales as a bit of a test now. 2/3 of Tassie is done, 25 sites up here, bunch of South Australia. They're the dots to cover the country. Conductivity information every 50 kilometres. So big program, lots to do. Getting some interesting results. These are Russell and Michael's major crustal boundaries across our model of Victoria. So the results out from here that Jingming, Carol and I are writing up at the moment, so we're going through that. So hopefully I've kind of convinced you that this sort of stuff is super critical for us to understand resources of Australia and Australia's natural environment, and not just resources but also hazards. We need to understand the Earth as a system, and the lithosphere is the major controlling aspect of the Earth as a system in the world in which we interact. We can definitely map the lithosphere, and hopefully people have started to see different ways we can do that. And we can also test it scientifically in the laboratory by looking at multiple data sets and even just by walking outside. Primarily in the history, and I didn't want to touch on it, but seismic properties are being used. So across the Earth, a lot of seismic properties are being used to understand the lithosphere, but there are other properties, and I showed you but one of the ways in which my PhD has kind of mapped aspects of the Australian lithosphere, the properties and also their uncertainties. So just because they're tools developed for looking at the whole of crust doesn't mean they couldn't be applied. Absolutely, my stuff is looking at depth of cover as well, but you look at really small windows for that. And also a way of actually quantifying magnetic character, something that also comes out of it that we didn't expect. And that's something for you to go forwards and do significantly more computationally based mapping of the Australian lithosphere. We need quantitative tools to do it. We can't continue to always just draw things with a pencil. We need to be able to quantify those things. And hopefully you can also see that we have a plan for how we're going to do this into the future using conductivity. So thank you very much for listening.